Hello everyone, I am Dr. Satyanarayan Rao and welcome to my video. In this video, we will talk about Laplace Transform. As always, we will talk about a brief history of how Laplace developed it, how it later developed into its modern form that we know it, and why it is such a powerful tool in mathematics and engineering. Laplace transform has numerous applications, for example in solving differential equations, analyzing electrical circuits. We will also see how Laplace transform compares to the Fourier transform and what advantages Laplace transform offers, especially when dealing with exponential growth or decay or transient systems. So just like today, we have a buzz around artificial intelligence where we see people debate whether artificial intelligence will do harm to humans or what impact it could have on the humanity. It was during Laplace time the Newtonian mechanics was well developed and it was clearly understood that how planets move. Like today we worry about AI's impact on humanity. Laplace was also concerned with a question that is the solar system stable, because we understand how it moves, but what happens if the orbits of planets are perturbed for some reason? Maybe an asteroid hit a planet or there was some perturbation, imaginative event. What could happen? Would it lead to two planets collide to each other, or would Saturn drift away from the Sun, or it would lead solar system into a complete chaos? This was the question Laplace had in his mind. So his interest was to understand how small perturbations affect planetary orbits over long periods of time. And this problem actually led him to study differential equations with perturbation terms. And so the technique he developed to solve these equations, the differential equations with perturbation terms, actually laid the foundation for what later became known as the Laplace transform. In the next section of this video, or in the next few minutes, we will see a simple example of how Laplace approached this problem and how the Laplace transform works. So let's consider a simple equation which is a simple harmonic oscillator equation, but with a small perturbation term, something like. So we have a simple differential equation now with a perturbation term here. It is a small perturbation term where epsilon is very small because planets are disturbed with small perturbations. And if this is zero, it means it's a simple harmonic equation, and now we have a perturbation term. And to solve this equation, what Laplace did was he defined a new variable, let's call it as capital X. And so he defined this capital X as small x plus omega. So this is how he defined a new variable that actually absorbs the effect of perturbation. So what happens now is our old variable now just becomes, if we find the first and the second derivative of this x, what we get is dx. For example, dx by dt is now dx by dt. Epsilon by omega square is constant, and d by dt of cos t is minus sin t, so we can write epsilon by omega square sin t. And so similarly, if we take the second derivative of x by t, then this becomes second derivative, and then sine again becomes cos. So sine will now become cos. And so now if we substitute this equation and the definition of x back into this original equation, what we get is something that is, it's a second order differential equation in terms of a new variable, the capital X, equal to 0. So this capital X now already has absorbed the perturbation impact, and our original equation something looked like a d. And so it's actually much easy to solve this equation as compared to this equation. And so by actually substituting or making a x absorb the perturbation, we now have a simple equation to solve, and this was the Laplace approach to actually solve the differential equation. We will see the actual problem, why it gets complex when we see many body dynamics within the Newton's gravity equation. So at the time Newton had given us the fundamental equation for the motion of our planet around the star that we have, which is the sun. So the equation looked something like t square. So the equation looked something like this, where g is the gravitational constant, m is the mass of the sun, and r is the position vector of the planet. And for a single planet and a single sun, this equation has a solution that is of an elliptical orbit, and it's very straightforward to solve if we have just one planet. And here r is the norm of the position vector. But the real solar system has multiple planets, and if we have multiple planets, we have then extra terms in the Newton's equation. And what it means is that, for example, the Newton's equation would look something like this. And so it will continue for other planets. And so as we include more bodies or more planets, the equation becomes more complicated. And if we add perturbations in third or the fourth planet, they will accumulate. And so Laplace actually wanted to know how this perturbation would cause the solar system to become unstable over time, and if they remained bounded, by cleverly defining a function that incorporated the positions and the momentum of the planets along with the perturbations, we could get the simpler form that we saw in the previous slides. But as Laplace thought about it deeper, if we have like a complex equations, for example a full gravitational problem that demands more general and systematic methods, so he wanted a method that could handle any differential equation in a uniform way. And this is where he discovered, or he developed a technique, it's known as the integral transform, that actually later developed into the Laplace transform that as we know as of today. And so let's see what is this integral transform before going into the Laplace transform. So instead of seeking a clever substitution like we saw in the earlier example, where we defined a capital X which actually absorbed the perturbation, what Laplace did was he considered an integral operation that would systematically transform differentiation in time into something very simple. So he defined a general function, something like f of s, where s was some variable, it's just a parameter, which is defined as integral of 0 to infinity an exponential of time e power minus st, and our time domain function here with dt. So here s is just a parameter, a real number, and that helps weight down the integral so that it converges. So applying this integral, actually, for example, if we have a differential equation like this, d square f by dt square. So if we apply this integral transformation to our differential equation that we saw in the previous slide, what we get is something interesting. It turns this differential equation into an algebraic equation. Very easy to prove, like we have to use integration by parts. And so finally what we get is something like s square f of s. So d square by dt square becomes s square f of s. So f of t becomes f of s minus some initial conditions. And so when we solve this algebraic equation, finally we can show that like the solution to our equation becomes something like g of s. And so we have turned a complex differential equation into a simple algebraic equation in the s domain. And so once f of s is solved, we can take the inverse Fourier transform to find f of t in the original time domain. And so this is the general method introduced by Laplace that now we use to systematically solve differential equation. So while Laplace discovered that the integral transform that we saw in the earlier slide that could convert differential equation into algebraic ones, he didn't realize that it could be systematically applied to all kinds of differential equations. So Laplace's focus was primarily on celestial mechanics, the stability of solar system, and the problem of Jupiter and Saturn, and understanding how planets orbit the sun and whether they were stable. But it was later Oliver Heaviside who was working on practical engineering problem like electrical circuits, because it was the era of telegram, and so these telegrams involved the usage of resistors, capacitors and inductors. And while Oliver Heaviside was studying electrical circuit, he developed what he called as an operational method. So he was actually unaware of Laplace's work, and what he did was he substituted the time derivatives that were involved in the circuit problems like charging of a capacitor or a induction in an inductor. So he replaced d by dt as a variable p, so that allowed him to actually transform complex circuit differential equation such as in RLC circuit into algebraic equations. So with algebraic equation, it's easier to analyze the transient response of circuits and to handle things like initial conditions, step functions or impulse functions. And interestingly, the later mathematicians who come after the Heaviside's work showed that the Heaviside's operational method that involved replacing the time derivative into a variable p actually was mathematically equivalent to the Laplace integral transform when the variable p was treated as a complex number. And what's interesting is that these two methods came from entirely different motivations. So while Laplace was actually solving the gravitational problem of many-body dynamics, the Heaviside, on the other hand, was driven by practical needs of engineering, particularly the electrical circuits. Both of these approaches actually unified into what we now know as the Laplace transform because of the work of later mathematicians. And so what started as a Laplace integral transform for celestial mechanics evolved through Heaviside's operational method for electrical circuits, and later mathematicians showed that they were essentially the same. Now we have seen the history of Laplace transform. Let's take a look at how it looks in its modern form. So the Laplace transform is defined as an integral between 0 to infinity of our time domain signal with an exponential signal e power minus st dt, where now s is a complex number with real and imaginary part. And so why this is powerful is, for example, when we take a resistor, inductor and capacitor circuits, the resulting differential equation, when we apply Laplace transform to it, it actually converts a complex differential equation into a simpler algebraic equation, which is actually much easier to solve as compared to solving a differential equation. For example, it's very easy to actually find a relation between current and voltage without actually solving the differential equation, because now we have the algebraic equivalent. So once we have the solution in the S domain in the algebraic form, we can always use the inverse Fourier transform to get the solution in our original time domain. And let's see how it is connected to the Fourier transform. As I said, the S is a complex number, but when we have the real part, sigma is 0, and when S is purely imaginary, it's nothing but the Fourier transform. Or we can say that the Fourier transform is a special case of Laplace transform when S is purely imaginary. And let's see the differences between the Fourier transform and the Laplace transform, what they can do. In the Fourier transform, what it means to have an imaginary exponential is that the building blocks are sinusoidal signals. That means the Fourier transform decomposes your time domain signals into the frequency content of the signal. It tells like which frequencies are present, like for example 30 Hertz, 20 Hertz, what are the frequency content, but it cannot tell us whether it was a decaying, sinusoidal or growth, any kind of transient response. We cannot know using the Fourier transform, but using the Laplace transform, it not only gives us the frequency content, but also it tells us that whether a signal is a growing system. For example, we can have a growing oscillation, and it means the system is unstable, and it occurs when sigma is greater than 0. And when sigma is less than 0, it means the signal decays. That means we have a decayed sinusoidal signal. And when the sigma is 0, it means the signal oscillates without growth or decay, which means it's the pure sinusoidal that Fourier transform can give us. As a summary, the Fourier transform, the basis function or the building blocks we use is a sinusoidal signal which shows the frequency content, but it doesn't tell us that whether the system is stable or it has a decay or a transient response. We have no information on those parameters. But in Laplace transform, we can actually find out what kind of decaying sinusoids we have in the system. So it captures both frequency content as well as the stability, for example, growth or decay. And none of this transform actually gives us if we have like a changing frequencies over time, at what time these frequencies occurred. And for that we have like a wavelet transform, but I will cover wavelet transform in another video. But as a short explanation, wavelet transform, we use the basis function as wavelets instead of either pure sinusoids as in Fourier transform or decaying sinusoids as in the Laplace transform. We use small wavelets or small packets of waves, which actually gives us not only the frequency content, but it tells us what frequency exists in signal, but also when those frequencies occurred. For instance, in a signal with changing frequency, the wavelet transform can show that low frequency component existed at one time while high frequency component existed at another time. This is because the wavelet transform uses small wavelets, short waves that are localized in both time and frequencies. So what I mean by time frequency localization is that, let's say we are studying a gamma ray burst. It's a very short high frequency event in a galaxy where stars or some black hole merges to give a burst of gamma ray energy, and this actually happens for a fraction of a second and disappears. And if I apply Fourier transform, it will tell me what frequencies are actually present in the signal, for example 100 Hz or 500 Hz. But the problem is it will not tell me when these frequencies occurred. So Fourier transform by its nature assumes that the signal is stationary, meaning that frequency content doesn't change over time. So it's a great tool for analyzing what frequencies exist, but it cannot tell us when the high frequency burst like this happened, for instance gamma ray burst. While Laplace transform on the other hand isn't useful for studying such variable frequency signal, because it can only tell us if the signal is growing or decaying over time, but it doesn't has the time information needed to detect transient events like gamma ray burst or other astronomical events. And now this is where wavelet transform is widely used in astronomy, because it uses small localized wavelets as its building blocks, and these wavelets can stretch for low frequencies or compress for high frequencies, and they can also slide across the time signal. This means that it can not only tell us what frequencies exist in our signal, but also when they occurred. So for example, if gamma ray burst happens, The Wavelet Transform is the ideal tool because it will tell me like when it happened and also what frequencies were emitted. And on the other hand, if we have a system like circuit or a bridge, if it is stable because of some oscillations, we can use the Laplace transform to check if the system has a growing or unstable oscillations or decaying or stable oscillations. And in a future video, actually, I will cover more on the Wavelet transform, and I also have a video on Fourier series, and if you haven't checked it, please feel free to go and see that video. And thank you for watching, and remember to keep learning and enjoy life. See you next time.